instead of breaking it up into rectangles like that, we're going to break it up into sectors. And let's suppose we want to find this area. See from the origin how it fans out this area? Let's suppose we want to find that area. And in this context, our textbook uses alpha and beta. Okay? So we want to find the area from alpha to beta. That's what we would run through our theta. This angle to that angle. To find that area. Well, I'll use this over here. You know, this is like theta sub 0, theta sub 1, theta sub 2, and so on. Does that make sense? Let's look inside, we'll put a theta sub k here. Let's look inside this one. This is your theta sub k asterisk. That's in between that sector. It's going right somewhere in there. You can imagine, instead of making a rectangle, there's like a piece of a curve up there. A piece of a circle instead of a rectangle. Okay? And that's theta asterisk sub k. So that's analogous to our x asterisk sub k here. The angle between two of these, that's going to be our delta theta sub k. And the distance, this distance from the origin out to there, that's going to be f of theta sub k. That's your r, that distance from there to there. So now, the area of that sector, we got to use this formula, is going to be 1/2 that radius f of theta sub k. It's actually f of theta asterisk sub k. Squared, that's that f of theta squared there, that's like the r squared here, times theta, which theta is this angle between them, that's the delta. Delta theta sub k, that is this theta. So times delta theta sub k. Now, that gives us the area of this sector. If you do that for each one of these and add them up, you have an approximation for the area here. Do you guys see that? That gives us an approximation. So, to approximate the area, well, we'll just do area. It's approximately the sum as k goes from 1 to n of this 1/2 f of theta asterisk sub k squared delta theta sub k. And then if we want to know exactly what it is, it'll be the limit as n goes to infinity of the sum 1 to n of this and When we have an infinite sum like that, the calculus tool that will do that for us is the integral. And we're going to use alpha and beta, same thing as a and b, just trying to be consistent with the book, of 1/2 f of theta squared d theta. That is the integral that calculates the area under a polar curve between one angle and another angle. So it's this area that gets fanned out below that curve. You guys all right with that? Any questions about it? You see how it's analogous to this? What you learned in first semester calculus? Okay. I'm going to erase the picture over there and I'm going to write one more thing on here. You ready? So, over here, we sometimes have an upper curve and a lower curve, and we find the area between two spots, right? Let's suppose this is f of x, this is g of x. And we find like an area like that. And the way we do it there is, from a to b, we do f of x minus g of x. Right? That's what we do there. For the problems we're going to do, this is all we need, right here. But you're going to, if you look in View an Example, or you open the book, you might see something a little different. In polar, it's possible you have, one of these things, and then you have like a circle or something else here. And your job is to find this area. That make sense? So this outer one could be, I don't want to put a dot on it, but the outer one here could be f of theta, and the inner could be g of theta. And so when you want to do the area of something like that, you'll do alpha to beta of 1/2 f of theta squared minus g of theta squared d theta. So if you have something like that, that's what you would do. We're not going to do any like that in our problems. So we're going to do some examples now. The hard part is not going to be calculating the integral. The hard part is going to be determining the bounds. Okay? Determining the bounds is going to be the difficult part here. The integral will be the easy part. You ready for that? Okay, let me erase this and we'll grab some out of the assignment.